All right, today's the 15th. What we're going to do is take a simple function, y equals x squared, a parabola, a parabolic path. We're going to define it as a vector-valued function. We'll find acceleration and velocity, and then we'll define the tangent vector, unit tangent vector, and principal unit normal vector. Okay, and I'll give you a way of doing the principal unit normal vector, which will cut out some of the work that's necessary to do that. So let's take a look at this. Here's a parabola. Let's define it as a vector-valued function. T squared. So that defines, like parametric forms, it defines an orientation. Okay? And you can instantly take a vector-valued function and change it to parametric form, where this is the x component and this is the y component. Okay, that's instantaneous. So for example, if you had to find the arc length of this parametrically defined path, what you would do is change it to parametric form and then use the form that we have for arc length of a parameter, right? That integral of the square root of x prime of t squared plus y prime of t squared dt. So that would be immediate. You could do that. What we want to do is take a look at velocity and acceleration, tangent to normals. Okay? Well, velocity, derivative of position, 1 and 2t. Okay? So if we're taking, let's take a look at the point 1, 1, say.
At least we have nice background music.
Yeah, that's true. That's true. That's true. Okay? At the point 1, 1, where t is equal to 1, we're going to get 1, 2. This will be our velocity, 1, 2. And that vector, that velocity vector here, okay? She accused us of having too much fun. Remember that time, that day?
I think we should have Tokyo bring his trombone and
Dude.
Really?
Yeah, we could have like a crazy band going on.
Wow.
The drums, right, Brandon?
Yeah, let's do this.
Wow. All right. This velocity vector is going to be tangent to the curve. There are times, however, when we want to find a unit tangent vector. This is a tangent vector, but a unit tangent vector is defined this way. It's r prime, the velocity, divided by the magnitude of r prime, the speed. Okay? It's velocity divided by speed. That's what the magnitude of velocity is. It's the speed. That's a unit tangent vector. And what that does, it makes a unit vector out of our velocity vector. So the unit tangent vector, in this case, okay, is 1, 2t over the magnitude of that vector, square root of 1 plus 4t squared. Okay? And in particular, at this point,
I feel like I'm in like another country right now. It's great.
I know we're in Bavaria or something in the Alps or something like that.
You
You
see
know?
like rolling hills right now.
Yeah. Whatever. T is 1, we get 1, 2 over the square root of 5. Okay? That'll be our unit tangent vector. Okay? Acceleration, the derivative of the velocity, okay? The second derivative of our position, okay? And that's going to equal 0, 2. And what this says is that the acceleration is a constant 0, 2 in the y direction. Similar to what Dan had, although this is a 0, 2, it stays 0, 2. That one at least changed, but it was only in the y direction, like this one is too. So the acceleration at every point is 0, 2. This is the acceleration. That's our acceleration vector at this point. It's our acceleration vector everywhere. Okay. All right. Principal unit normal vector. Okay, this is what this is called. This is the principal unit normal vector.
So the velocity or the tangent vector lies on top of the velocity.
Yes. Yeah. They're always parallel to each other.
But they wouldn't be the same coordinates.
Not necessarily the same, because the unit tangent vector is of length 1. This is the principal unit normal, and the reason why it's called the principal... What's that? Oh. The reason why it's called a principal unit normal is because there are 2 normal vectors to this path. There's one pointing inward. I'm going to extend it out a bit. This is the one we want. That's the principal unit normal vector. And there's another normal vector, bless you, okay, which is the one we're not interested in. It's a normal vector. It's perpendicular to the tangent vector, but it's not the one pointing inward in the direction of motion, and that's the one we're interested in. That's the principal unit normal vector, the one pointing inward. That's equal to t prime, okay, over the magnitude of t prime. Okay? That's its definition. It turns out, however, in many applications, it's complicated. It's difficult to use. It's difficult to apply. Watch it right here. This is a pretty simple path here, this parabolic path. But what happens when we start trying to figure out the principal unit normal vector? Well, let's see. It's equal to t prime. Now here's t. T prime is the derivative of this. And to take the derivative of this, we have a quotient rule with the square root. It gets messy. Fortunately, there's a trick to this. Okay? You ready for this?
Mr. Burns, I don't get this.
You don't get it? Then drop the clap. Withdraw. Is that what you tell him?
That's recorded there, huh?
Oh, jeez, yeah. Oh, jeez.
YouTube's gonna be able to hear that.
Oh, well. Shoot. All right. Jeez. All right, the little trick for this is to do the following. Here's what you do. You swap the components of the unit tangent vector. Swap these components. 1, the 2t and the 1. I'm going to swap them. So this becomes 2t and a 1 divided by that scalar quantity here, that constant, or that magnitude. But you're not done. You got to swap the components, and then what you must do is take the opposite of one of them. Okay? If you take the opposite of one, you'll get the principal unit normal. You take the opposite of the other, you get the other normal vector. Okay? So what you have to be able to do is take the opposite of the correct one. Now, the principal unit normal is the one that's going backwards this way. So which component should we take the opposite of? The x component or the y component? The x. The x component will have it moving backward because the x is now negative, moving backward. This is the principal unit normal. If you had taken the derivative of this, 1 over this, and the derivative of that, okay, this quotient rule, and then divided by the magnitude of that derivative, you would eventually get to this. But it's a lot of algebra to get there and calculus to get there. You definitely want to do it this way. What I do want to do is prove that this is indeed normal to the unit tangent vector. And how am I going to do that? We can prove it's normal to the unit tangent vector by doing what? Not across. take a dot. If we want to take the dot product and have it come out to be what? To show that the two are perpendicular to each other. 0, that's correct. Because that'll give us the cosine. The cosine is a dot product over the product of the magnitudes. And if the dot product, the numerator of that, is 0, the cosine is equal to 0, and we have a 90-degree angle. Hence, they're normal to each other. So what I want to do is take this normal and dot it with the tangent, and let's see what happens. Let's take the tangent, dot the normal, okay? And that's the whole point of swapping them and taking the opposite of one of them, because what happens here is, here's my tangent vector. Dot the normal. And what happens is we end up with negative 2t, positive 2t, 0. Okay? That shows that they're indeed perpendicular to each other or normal to each other. Okay? Okay, one other thing I want to do here. Go ahead.
For a more complicated function, how are you supposed to know which one you're going to make negative?
You're going to have to graph it. And I'll tell you, if it's a more complicated one, that would seem to imply that this calculation of taking derivatives divided by the magnitude of the derivative is even more complicated. So you want to get the plot of the function. The alternative is to do the algebra out, and it's just really bad. Or you do it in Mathematica. Maybe that's the real alternative. Mathematica will take care of it.
Can you go back
Oh,
to the
yeah.
drawing?
What do you want to do?
Can you just go back to the drawing?
Oh, yeah.
What's that vector that's not the tangent vector?
That's the velocity. Here's what we got.
Yeah,
We got a velocity vector.
Yep.
We got a unit tangent. We got the acceleration vector.
Oh.
That's A here. That's A1. It's over here somewhere. Yeah. All right. Sorry.
That's okay. That's all right.
Okay. There's one more thing I want to do. I'm going to redraw it too. Okay. What we want to do is find the normal and tangential components of the acceleration. All right? So here's what we're going to do. Watch this. Okay, you guys all set?
All right.
Okay. Let's take a look at this. Let's suppose we have a vector valued function traveling along a path. What we're going to have is a unit tangent. We're going to have a principal unit normal vector, like so. We're also going to have an acceleration vector. Maybe something like this. Okay. We also have a velocity vector I'm not going to draw, which would be part of this unit tangent. It's possible, it's conceivable that it's less than, its magnitude is less. It's also conceivable, which usually what happens is magnitude is greater. Okay, but that's what we have. Now, what we want to do is find what are called the tangential and normal components of acceleration. Okay? And what these are is the magnitude of the projection of the acceleration on the tangent line okay. That's the tangential component of acceleration. It's denoted this way. And then you have the bless you. The normal component of acceleration, That's the magnitude of the projection of the acceleration on the normal line. Okay? It's how much of the acceleration is directed along the tangent line and how much of the acceleration is directed along the normal line. Okay? You got a satellite going around the Earth. Okay? You got the same thing here. That satellite is tending to move off along the tangent line. Earth's gravity is tending to pull it into the Earth. You've got the same situation. How much is the acceleration along that tangent line? How much is it along that normal line? Okay? So, let's find out. Let's do it. So, tangential component of acceleration is the magnitude of the projection of the acceleration along the unit tangent. That's what it is. Now, what's the magnitude of a projection of one vector on another?
Dot product divided by magnitude squared?
Yeah. What? Yeah. Good. Except for one thing.
Times the.
Well, yeah, but that's the whole projection. The magnitude of the projection is the dot product divided by the magnitude of the vector projected upon, not squared. Yeah.
It's already in the vector.
Yeah. Boy, you guys are good. Okay, so it's dot product over the magnitude of t squared. No, it's not squared. I just said it wasn't squared. Oh, let's see.
Got us.
Oh, boy. All right. A dot t. What's the magnitude of t? The unit tangent vector? What's the magnitude of a unit tangent vector? 1. Thank you very much. Okay. That is the tangential component of acceleration. It's a dot t. It's the length of this vector here, or the length of this projection of A on T. Let's do A, projection of A on N. This is the normal component of acceleration. It's the magnitude of the projection of A on N. It's A dot N over the magnitude of N. The magnitude of n is 1. We get A dot n. Okay? Okay, you with me? Okay. Now, if we were to take, I'll give you an example in a minute, but if we were to take the tangential component of acceleration and square it, and add to it the square of this normal component of acceleration, what should we get? If I were to take this, square it, and add it to the square of this, what should that result be? What is it? No?
Square of 18.
The square of acceleration. That's exactly what it is. Okay? It should be the square of the acceleration. Because what you've got here, this and this are going to be the same. So you've got this right triangle here, or this one and this one are the same. Here's your acceleration. We've got this distance or length. It's the magnitude of that projection. You got this same as this. So this squared plus this squared should be that squared. So let's do it. Okay, you ready? Let's go back to the previous example. Y equals x squared, and we're going to do this out. Okay, so in our previous example, we have this. Okay. We've got our point. We've got our function. Am I still on there? Yep. We've got a point 1, 1. And what we found is that t is equal to 1, 2t square root of 1 plus 4t squared. We found the normal to be negative 2t, 1, square root of 1 plus 4t squared. We have our acceleration vector, which is equal to 0, 2. Let's do the two components. Tangential component, A dot t. So we get 0, 2 dot t, 1, 2t over square root of 1 plus 4t squared. That's equal to 4t over square root of 1 plus 4t squared. That's a tangential component of acceleration for any value t. Let's do the normal one. A dot n. Okay, and we end up with 2 over square root of 1 plus 4t squared. Okay. And here's what should happen. You ready for this?
Not quite.
Not quite. Okay. I'm not sure I am either. Hopefully this is going to come out right. All right, let me draw some things here. Here's our unit tangent. Principal unit normal. I'm going to prove it for all t. I'm drawing it at t equals 1. We have our acceleration, which we know is 0, 2. Okay, this is our acceleration here. That acceleration of 0, 2 is true everywhere along this path, not just at this point. Okay. And here's what I want to show, that if we take the square of the tangential component plus the square of the normal component, we get the square of the acceleration, the magnitude of acceleration. So let's do it. Are we ready? Dave's ready. Oh, Dave's ready. Tim, are you ready?
All right, I'm ready.
Wait, Teddy's ready now? All right.
We can wait for Tim and
All right, here we go. So let's take tangential component of acceleration squared. That is a real number already. Okay? Let's take the normal component of acceleration and square that. And we should get the magnitude of acceleration squared. Okay? Just to verify everything. So let's do it. Tangential component of acceleration is 4t over square root of 1 plus 4t squared. We're going to square that. Plus normal component of acceleration, 2 over square root of 1 plus 4t squared. We're going to square that. Thing is it equal to the magnitude of acceleration, which is, this is 0, 2, so its magnitude is 2. Is that equal to 4? Is that possible? That's equal to 4? Holy mackerel. That seems highly unlikely. All right, doesn't seem possible. What do you think, Janish? Would you be betting on it?
Yeah.
You would?
You already did it.
All right, wait a minute. Let's bet. I'll bet you 20 it doesn't come out. No. Let's do it. So we get 16t squared over 1 plus 4t squared plus 4 over 1 plus 4t squared. Is that equal to 4? Well, let's add them up. We got 16t squared plus 4 over 1 plus 4t squared. Is that equal to 4? Let's factor out a 4, and when we do that, we're going to get a 4t squared plus 1. I'm going to reverse this. 4t squared plus 1, and that is nuts. 4 equals 4. Okay? And it works. All right.
So you should expect the t's to factor out or to cancel each other.
Yes. Yeah. In that particular example, you should, because of the way the acceleration came out to be 0, 2, and its magnitude is a constant 2 squared, which is 4. So it had to. So no matter where you are on that, that's going to be true. Those will cancel out for any value t. All right, so here's what we have. Unit tangent vectors, okay? Principal unit normal vectors. We've got normal and tangential components of acceleration. We still got a couple things to do. One thing we have left to do is curvature, okay, which I'll define tomorrow. It's the magnitude of t prime over the magnitude of r prime. It's how fast the thing is turning, okay? It's very important for Mathematica and how Mathematica plots its graphs. It takes more points, samples more points with higher curvature. If it's turning faster, it takes more points here than it does where it's more linear-like and things are not changing as fast. And then I'll also mention osculating circles, which are the kissing circles. In my room, when you go to my office, the whole wall is kissing circles, osculating circles. And osculating circles are those circles that are tangent to the curve, but the radius of an osculating circle is reciprocal of the curvature of the curve at that point. The more the curve looks linear, the greater the radius of the osculating circle. The less curvature that curve has, the more linear it looks like. The curvature of a straight line, okay, is 0. There's no curvature. The radius of curvature of the osculating circle is infinite in that case, okay? And as the thing bends, okay, and the curvature increases, the radius of the curvature of that osculating circle decreases. I'll talk about it.
What did you say the curvature was first?
The curvature is how fast the thing is turning.
Right.
A straight line has 0 curvature, but it has an infinite radius of curvature of its osculating circle. We'll talk about it tomorrow. We got a test when now? Thursday. Next Thursday. We're almost done. We're just about done with this chapter. We're good. No, David, let's go do it. Let's go do it right now.
I have a question.
Wait.
How did you get